So this is the first video now in our third module set. This is the focus of this section is on something called derivatives. And so there's actually 6 topics in this section. It's a larger one than we've been doing in the past. The 6 topics kind of start off with basic principles of derivatives. They go through some pretty important rules for how to find derivatives and then how to do things like add and subtract, multiply and divide them. A very important rule, I believe, in topic 5 called the chain rule, which when I talk to university people, especially the professor that I had asked earlier before the beginning of the semester, he said chain rule is like one of the most important things you'll learn. So we're really going to focus on that in that particular lesson. And then we're going to end with a topic on, I believe, implicit differentiation. So those are our main topics. This should take us 3 weeks. The advice I want to give during this section here before we get started is please don't leave the video watching till the last little while. I know some of you have a tendency to procrastinate, but that is not helping you going forward. I'm sure you probably know this. You don't need me to nag you on this, but watch the videos sooner than later if you can. This section here may require a little bit more practice than you've been doing otherwise. I'll try to give you some examples if you'd like of places to look. I'll find you some worksheets online or some textbook questions for practicing doing some derivatives, because this is one of the few sections where you're really going to want to get your reps in. You want to do some repetitions on doing derivatives, because this is kind of the meat of calculus now. This is kind of like the main section. A lot of the first couple of sections that we did, I was always talking about how there's like a trick to it where you want to try to solve the little puzzle. This one right here is more skill building, where we can spend some time where I could give you questions 1 to 30. And you could just really do lots and lots of practice questions, just get the hang of the pattern. Whereas the previous 2 units were more of a puzzle-y, trying to show off your algebraic skills. So, anyways, that kind of intro being said, let's get started talking about derivatives. So, we've actually used this notation before in the previous section on limits. This is the definition of a derivative. The derivative can be written as, and this is the notation we use. We can write it as f with a little dash up in the corner x. This little dash is known as prime. That's kind of the vocabulary we'd use for that little dash. So we call it f prime x. That prime didn't show up very well there. The derivative, that's what it's known as, is really this notation, which is the limit notation as you get close to a point. Really, this is what we did back in the tangent. Set of notes in the previous ones here. What we were actually doing, we didn't know it at the time, but that we actually have a name for that concept. We call that finding a derivative. And I had to work very hard during topic 3 of the last section to not call it a derivative. I always had to try to specifically say we're going to look for the tangent line at a point and talk about it in terms of tangents. But a derivative basically is an equation that will find you a tangent at any point. And that's what I actually have written down here. Whenever we were solving for tangents along the like tangent slopes at any point here, we were actually finding what was called a derivative. So for a starting section here of our derivatives, we're actually not doing anything all that different than what we were doing in the previous section. We're just going to continue to build on it. So just as a quick reminder, the idea that we had in the previous section is that if you have some sort of graph, like for example, we were to plot the, let's see, how much work you had over how much time had elapsed, and I wanted you to calculate the slope at this point right here, the tangential slope at that point would be, we actually have a name for that now, we would call that the derivative. That's the word we use, the derivative. And while I'm thinking about this right now, there's a lot of different adjectives we'd use to describe that. Sometimes we would call it a derivation, or sometimes we say that it's differentiation. Those are some words that we'd use to describe basically taking a derivative. And taking a derivative just basically means find me the slope right here. I chose work and time because for any of you who know your physics, the slope of this graph is going to be the power, because power is work over time from a physics point of view. So the derivative of work and time is power, and the way we would notate that is W for work, prime, T, This basically is you're taking f of x. If you're taking the function where you're doing work as a function of time, if you find its tangential slope, that's actually known as the power. So, and we had a couple ways of solving it. One was the q minus p sort of method, where you had like f of q minus f of p over q minus p. The other one was the AH method. Both will work here, but essentially this right here, its new definition now is it's a derivative. So I want to build on that today. So that's what we have just written on the slide here. Remember, the slope of a tangent line can be calculated using this formula, and that slope is a derivative, except here's the big difference here. We're not going to substitute a value for the x variable. Okay? I'm not actually going to tell you at what point we're looking for. In the previous examples that we would have done on the assignment, I would have asked you, find me the tangent at the point x equals 3. And then this would have been like a 3 right here. We're not going to do that today. We're going to do this at a general point. And you actually had a question on your previous assignment where you had to solve it at the general point. I believe it was just A. You had to just work with letters all the way through. And so that question off the assignment, number 7 or 8, whichever one it was, hopefully you've tried it already, that actually is the definition of a derivative. It is a derivative doesn't just tell you the slope. A derivative is an equation which will tell you the slope at for any point, not just one x value, but any x value. So it may work best just to give you an example here. Here's the other definition of a derivative. You could do f of x minus f of a over x minus a as x approaches a. This really is a fancy way of doing the p and the q and the p and the q and the p and the q notation. You can do that as well. So either of these will work. You can either use the PQ notation or the X and A notation or H and A notation. Honestly, they're just letters, right? Who cares what letters you use? Okay. So let's do an example. We're going to find the derivative of these functions here. So I've just got some basic ones to begin with. So if you want to find the derivative, here's the new way I'd like you to describe it. The derivative notation means you're looking for f prime of x. You're looking for an equation of the slope. That's what we're looking for. So it'll find you the slope, but at any point. So that'll be equal to, and we used this notation previously, it's the limit as h approaches 0 for f of a plus h minus f of a all over h. That was kind of our main notation, which I believe is what I wrote way back here on this slide here, only rather than using a, which is a value that we would know, like we're going to know that a is 2 or that's 3 or 4 or 5. I'm going to leave this a value right here as an unknown. It's going to be an x. It's for any x value. So the one subtle change I'm going to make here is rather than throwing in a's there, I'm going to leave x's. So I don't get to go like 2 plus h and f of 2. I have to leave it as an unknown x. All right, so let's fix this up here. So the limit as h approaches 0 for f of x plus h minus f of x all over h. So here's how that would look. I'm not able to plug in h as 0 just yet. That's not something that's valid, because obviously I can't divide by 0. The denominator can't be 0. But what I can do is work with the equation. So the equation is going to be f of x plus h. Well, that just means go x plus h squared, right? I'm just taking the x plus h and plugging it in here to the function. And then I have to minus f of x. Well, f of x just means x squared, right? Because the function is just x squared over h. And at this point, I'm still kind of stuck. I can't plug in h as 0. So I have to maintain my limit notation. And I'm going to distribute, which should give me x squared plus 2xh plus h squared. I'm still going to minus the x squared that kind of finishes off the thing over h. And for those of you who, hopefully you've all done that question I'm talking about on the assignment, I don't get numbers to work with. This is where the challenge becomes now, is I'm working with letters the whole way through. But you should discover that the trick happens here where the x squareds cancel. And you're left with the limit as h approaches 0 of 2xh plus h squared over h. And now you're going to see the trick, hopefully, is that all of these terms have an h in them. You can actually do some canceling, and you'll be left with 2x plus h. Well, now there's no reason why you can't plug in h as 0. So I'm going to do that now. It's now 2x plus 0. And so my final answer, this is the derivative. F prime x, the derivative, is 2x, which basically is an equation. If I now want to find the slope at any given point, you just have to tell me what that point is. Do you want the slope at 5 or 6 or 7? I can give you the slope right now. Okay. Let's talk about this graph real quick. Here is the graph of the good old x squared parabola. Okay. Let's say you want the slope of this graph at 0. Right? 0 would be right here. And hopefully if you kind of consider what the graph would look like, well, pretty sure it'd be just a horizontal line, right? And using my derivative equation here, if I plug 0 in for x, 2 times 0 would give me a slope of 0. That makes sense, right? Well, let's say that I wanted you to find me the slope when x was 3, which might be, say, over here. Well, hopefully you'd agree that the slope of this line right here should be a fairly large positive value, right? Well, I can tell you right now the slope of that is going to be 6 then, because 2 times 3 will be 6. And yeah, that sure looks like the slope could be 6 there. Right? Let's say I wanted to find the slope at -1. Right? -1 is right here, right? Well, then I can tell you the slope at that point is going to be -2. Not quite as steep as it was over here, because it's 2 times -1 gives -2. So, long story short, a derivative is not just the slope at a point, but it's the equation which can provide you the slope at any point, so long as you tell me which x value you want. So, let's try another example. Like I always say here, rewind, watch videos again if you need. But let's try another one here. Let's see whether you guys can follow the second one here. I'm just going to erase all my work so I have some space. Because you probably noticed by now, you're going to require a lot more room to answer questions. Like my answer keys, just so you guys know, are often like 10 pages plus. If you're trying to cram all this into like a little bit of space, you're not doing yourself a service. You should really, you should make sure you save yourself lots of room. So, okay, to find a derivative, the formula is, it's the limit as h approaches 0 for f of x plus h minus f of x all over h. And again, if you're kind of, right off the bat, if I'm losing you as to where this formula came from, go back and rewatch last unit's topic 3 video. Okay, you're going to want to watch that one because that was the video that kind of talked about this formula, only we used a's and h's. And we used numbers for all of these x's, like you could plug in a 3. The idea now is, again, we're going to do this for a generic unknown x point. So this is going to be 2x plus h squared minus 5x plus h plus 6. See how what I've done is I've plugged x plus h in for all the x's. And then I'm going to subtract the function as written. I'm going to distribute the negative all in one step if I can. I'm going to make it 2x squared plus 5x minus 6. And hopefully I don't lose you on the algebra there, because really I should be subtracting this. I'm going to throw a negative in front of all of it and distribute the negative and flip the second 2 terms. This is all over top of h. Right? Ideally, I'd love to plug in h as 0, but I can't yet, so I got to kind of keep processing the algebra. So this is going to give you 2x squared plus 4xh plus 2h squared minus 5x minus 5h plus 6 minus 2x squared plus 5x minus 6 all over h. Okay, if I lost you on the algebra, relook over that section there. Make a note if I lost you on that stuff there, so you can ask me later in class. But ideally what should happen now is there should be a whole bunch of canceling. Watch this. 2x squared can cancel a minus 2x squared. Minus 5x can cancel a plus 5x. 6 can cancel a minus 6. What we are now left with is the limit as h approaches 0 of 4xh, 2h squared, minus 5h, and it's all over h. Well, again, the same thing happens a lot if you're doing it properly here. All of these terms have an h, so you should be able to cancel. And it leaves you with 4x plus 2h minus 5. Now you don't have a problem anymore. There's no reason why you can't plug in h as 0. So let's do that. Now you don't need to write your limit notation anymore. So it's now 4x plus 2 times 0 minus 5. Which means that my derivative, which we write as f prime x, my derivative is 4x minus 5. This is an equation which will tell you the slope at any point. Right? So keep in mind, this original graph we had here that we started with was, let's see, it was 2x squared minus 5x plus 6. So I don't know, probably looks roughly like this. I'm just spitballing here, right? Well, this is an equation that will tell you the slope at any point you want. So if you want to know the slope over here at negative 7, just plug negative 7 into this guy right here. 4 times negative 7 is minus 28. Minus 5 more, it means the slope would have been minus 33. Yeah, that could be my slope of minus 33. So that is what a derivative does. And again, the whole point of a derivative is to help you find an equation for the slope at any given moment, because in so many different applications of calculus, which is why calculus is needed for engineering and for medicine, especially in the biology fields, and it's needed even in economics, is that if you've ever got a rate of change where you might want to figure out work in relation to time and you might want to find that slope, well, a derivative then is an equation that will find you the slope at any given moment. Right here, the slope is positive. Right there, the slope is negative. Right here, the slope is 0. Right here, the slope is positive. Right? Hypothetically, if you were an investor, so you're thinking economics, and you're wondering, why in the world would I care about this? Well, if this was you plotting how much money a stock was over how much time there was, right? The derivative, well, we would want to consider where the derivative is negative. Because where the slope is negative, that's not good, right? Like right here where you have negative slopes, that's not a good thing, right? Because you are now losing money over those courses of time, right? Where the slope is the greatest, like right here, for example, the slope at this point right here is pretty steep. Well, that's good, right? Because that means that your stock on a day-to-day basis is making the most money on a day-to-day increasing gain, right? Like from day 53 to day 54, right? Over like a 1-day gain, it looks like it gained the most it possibly could, right? So hopefully you can kind of envision how these derivatives would be useful. So let's try one more example here, only now what we're going to do is we're actually going to find the slope when I give you some values. So we'll do one more example here. And one idea is, if you'd like to, maybe try it before I do it. Now try the example yourself, because I've done a couple, and see whether you can get it before I show you in the video. So maybe pause the video. If not, just watch the video and follow along. So a derivative, which is this notation here, is equal to, again, the limit as h approaches 0 for f of x plus h minus f of x all over h, which is going to be equivalent to x plus h squared minus 3x plus h. Then we have to subtract the function, which means we have to subtract x squared minus 3x, which again means I'll have to distribute the negative. So don't mess up the distributing the negative part there. Okay. As I look at my work right here, I really have been sloppy. I should have written that limit notation in there, because I don't remove that limit notation until I actually substitute x as 0. So hopefully you're able to follow my algebraic steps right here. I mean, basically at this point, it's just distributing. You have to have solid algebraic skills, obviously, to go on in calculus. But hopefully you'll discover that those guys cancel. These guys cancel. And we are left with a whole bunch of terms, and all of those terms should have an h in them, which is kind of the point. Because if you have a 2xh, you have an h squared, you have a minus 3h over h. What we can do is we can cancel out those h's. Now I'm still going to need to write that limit notation because I haven't actually replaced h with 0 yet because I can't, right? But this should be 2x squared plus h minus 3. And then on my next step, now I can replace my h with 0, and so I'll leave it there. This is my derivative. An equation which will find the slope at any given point. But this question had one more part to it. I actually asked you to find me the slope of the tangent when x was 1, 2, and 3. Well, now all I have to do is to find the slope when x is 1. Just plug in 1. So when x is 1, the slope is minus 1. When x was 2, the slope was 1. And when x was 3, the slope was 3. Okay. So if I were to say this was a graph again of like, say how much money you were making over time, and if I were to ask you, were you making the most money on day 1, day 2, or day 3? You'd say you had the greatest rate of change on day 3 because on day 3 you had a slope of 3. You were making money at a much faster rate than you were on day 2. On day 2 you were making money as a slope of 1, and on day 1 you were actually losing money, right? A negative slope means you would have been losing money. So, okay. So this particular slide, I don't know how it turned out in your notes here, but just so you're aware, these boxes right here should be delta symbols, just so you guys can make that change here. It seems like it's auto-formatted things and it's taken out the delta symbol. So here I'm basically trying to describe for you then the whole purpose of a derivative. We can then find the derivative f prime a or f prime x. It's the equation for the slope of a tangent at any given point here. But the other way we can interpret it is like I've been describing in like a physics or a real-world applied point of view. It can be found as the rate of change. If you ever have a graph where this is your rise over your run, like for example an acceleration on a velocity time graph, if you have velocity time, the slope at a given point is the acceleration, then you can find that as well. It's the same thing, right? So you are going to get some word problems then, is what I'm trying to get at next. Is I'm going to throw some elementary physics and economics at you over the course of this course, where you need to find the derivative. And the derivative is kind of like bumping it up to the next level. It's if you have distance, the derivative of distance would give you velocity. The derivative of velocity would give you acceleration, right? So anyways, let's try an example here. You throw a ball up in the air, and I give you the distance of the ball from the thrower. So this is a function of how far the ball is from you as you throw it. So if I want you to calculate an equation for the velocity at a general time, really, part A, I'm just asking you in fancy words to find me the derivative. So we're just doing what we were always doing before, right? Find the derivative. So, I mean, you can work with T's or X's or A's or H's. It's all really the same letter. So the formula for that would be the limit as h approaches 0 for f of x plus h minus f of x all over h. Started writing a t there. Should be consistent. Either use x or use t, but don't do half of them with x and half of them with t. That would be poor. Don't forget to include a negative so that you distribute the negative, right? Hopefully you're able to follow this. I'm really not narrating anymore because I've done like 4 examples of this at this point here. Okay, this should give you negative 5x squared. This should give you negative 10xh. It should give you negative 5h squared. You should have 20x and 20h. And then you should also have 5x squared. you should have minus 20x. It's all over h. And then you should discover, boom, 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 a whole bunch of stuff cancels. Okay, so I've got some good news here as I kind of start narrating again here. If you're doing it right, you will know, because you'll just bang, you'll see, wow, everything canceled. It worked out the way it should. And on your next step here, you should discover that everybody in the numerator should have an h in it, which means you should be able to cancel out those h's by factoring and selectively removing it. Now you have no more problem in the denominator. So then actually plug in h as 0. This is your equation for the derivative. So if you want to find the velocity then at any given moment, which is really what the part question asks for, this is the equation for the velocity at any given moment. Well, if I want to find the velocity after 1 second, we'll just plug in 1 second. So I might call this like f prime t, and that is the velocity, and it's equal to negative 10x plus 20. If I tell you that the time is 1, then your velocity is 10. So at 1 second, your velocity was 10. At 2 seconds, your velocity would be something different, right? At 2 seconds, you'd actually have no velocity, because if you put a 2 in here, negative 10 times 2 would be minus 20, cancels the 20. So hopefully you can kind of see how the overlap here works between the sciences and the calculus. If you have a graph, and on your graph, if this rise over this run, if it's purposeful in some sort of way, then the instantaneous slope, a derivative then is an equation for that, basically anywhere along the way. So, what I may ask you to do then is try to sketch a graph of what a derivative might look like. And this is it's kind of a, you just got to wing it by hand sort of task. There's no like I'm not looking for this to be done exactly. This is more of like a rough concept. Okay, so I mean, you can do it wrong. Okay, like you can totally be out in left field and not do it properly. But there's, since we're not going to do this exactly, and we're just going to do it by hand as best we can. If yours looks a little different than mine, that would be understandable. So I'm going to talk about just a few key points. This key point right here, this key point right here, and this key point right here. Because those key points right there, the slope of the tangent for all those points would be 0. So with a new color, that would mean on my next graph, those are going to have to be intercepts, because the slope of that is 0. Right? The slope right here was 0. So hence, on my new graph, I'm going to put a 0 as my slope. Right here, my slope is 0, so I'm going to put a point on there at 0. And right here, my slope is 0. Then I'm going to consider, just kind of erasing a little bit here. Then I'm going to consider where I have positive and negative slope. Right here, hopefully you'd agree, I have positive slope, right? Like right here, there's a positive slope. Right here, the slope is still positive. Right here, the slope is still positive. Right here, the slope is still positive, but hopefully you'd agree, the slope of this point right here is kind of becoming less positive, right? Like here, the slope could be positive 6, then positive 5, then positive 4, then positive 3, then positive 2, then positive 1, then 0. So really what's happening here is we have positive slope. I know the values right here, the values themselves right here are sometimes in the negatives, but hopefully you'd agree, the slope right here is positive. The slope there is positive. The slope is positive, but that slope is becoming slowly but surely less positive until right here where the slope is 0. Then during this section right here, the slope is negative, right? Here the slope is negative, here the slope is negative, here the slope is negative, here the slope is negative. So we're going to have some negative slope for a while. But eventually that slope, although it's negative and it reaches a certain negative value, eventually like somewhere in here, that negative slope starts to slow back down again. Where here you have a slope of say negative 2, and then a slope of negative 1, and then slope of negative 0.5, and then eventually gets back to a slope of 0. So eventually it kind of turns around and comes back to 0 there. Well, then you start having positive slope again, and boy, you start getting some pretty big positive slope. Here's a slope of positive 5, But then eventually you get a slope of, well, +4, +3, +2, +1. Really, the slope then, if I can kind of just draw just one graph here, the slope becomes positive again, really, really positive for a little while. But then the slope starts slowing down until eventually you still have positive slope, but eventually the slope becomes 0. Right here, the slope is 0. Right here, the slope is 1/2, hence the y value of 1/2. Well, now you've got negative slope again, right? And really, the remainder of this graph right here is negative slope, right? So this has not a whole lot of negative slope, right? This might have a slope of -1/2. There's -1/2. And then right here, I might have a slope of -1. Well, now we're down to -1. Over here, I might have a slope of -2, down to -2. Here, I might have a slope of -3. Really, the negative slope is getting larger and larger. And so it wasn't my greatest drawing here, but this is a rough drawing of the derivative. Keep in mind, the derivative is an equation, right? Now, I want to talk about something here and go back here. See how here I had a quadratic? Well, a quadratic has a derivative which is linear. This graph right here would have been a quartic. It has a derivative graph which looks cubic. General rule of thumb, the derivative is 1 power less than the original. Quadratics have derivatives that are linear. Cubics have derivatives which are quadratic. Quartics are cubic, and so on. So, okay, this was a pretty challenging task here. You may want to rewatch the little snippet of video here, and if that still didn't make sense, you're going to want to ask me some questions about how I kind of did that, because this is the sort of thing where if I had a regular classroom, I'd probably do like 3 different examples, and I would literally like sit next to you side by side, and we'd talk through it like point by point by point. What's the slope right here? Well, you might say the slope right here is 7. Well, then right here on the new graph, that's now at 7. And like right here, I might say, well, what's the slope? And you'd say, well, the slope right there is 0. Okay, well, on the new graph, then the number right there is at 0. For your y values, by the way, right? Like your y values are your outputs. So, okay, at certain times of year, this actually really matters when you get close to, like, say, the solstices or the equinoxes. I like using this as an example in terms of maybe trying to understand what a derivative is. Okay. Right now, when I'm making this video, it may not be the same time of year as when you're watching it. But hopefully you guys know the longest day of the year and the shortest day of the year. And if I were to plot them on a graph, it's like a sinusoidal curve. Here's the longest day of the year in June, which usually it's what, like June 21st or so? That's your longest day of the year. And your shortest day of the year is usually about December 21st, right? I want to focus not so much on those days, but I want to focus on the equinoxes, which are somewhere in here and somewhere in here. And like one of the equinoxes, I believe, is on about March 21st or so. What's the other one? I think it's September 21st. Those are the equinoxes. And you can actually see this in the daylight, right? What ends up happening is on a day-to-day basis, the amount of daylight, the change in daylight per time starts to increase, right? Right here, the slope of this graph is very, very slow. Like, are we getting more daylight on a day-to-day basis? Yes, we are. In January and February, you slowly but surely start getting back more daylight. And then in February, it gets better. And in March, it gets better. And right around March 21st is when the slope of this graph is the best it's ever going to get, right? Hopefully you'd agree. Right here, the slope of this graph is about as steep as it's ever going to be. What that means is, in the month of March, on a day-to-day basis, the amount of daylight you get, the change in daylight, right, the delta daylight, the change in daylight you get per day is probably the most it will ever be. And you can visibly see that, right? Like on March 1st to March 2nd, the sunrise amount changes by like 8 minutes a day or something like that, right? Where one day it's at 6 o'clock, then it's at 6:08, then it's at 6:12. You can actually see big changes on a day-to-day basis. Whereas once you start getting back into February, April, May, June, you don't really notice the change as much anymore. Are the days getting longer? Well, yeah, you still have a positive increase. Your days are still getting longer, but it's not as drastic, right? So if you can consider it to be the change in daylight per time, how much change you get per day, right around February, March, April, you've got the biggest increase, right? And you can feel it, notice it. If you're anything like me, around March, you stop having like those days where like you go to school in the morning and it's dark, and you come home from school and the sun's almost setting, where you get to a nice spot where it's like, wow, the sun's up already, and you can actually notice a change. When I'm driving to school in the morning, I'm usually driving westward, so I don't get the sun in my face. But sometimes when I'm leaving town for a brief little while, I'll have the sun in my eyes. But usually the sun is only in my eyes for just a couple of days, because sunrise changes so drastically every day that if I'm always leaving for school at say 7:30, the sun might be in my eyes for only like 1 or 2 days. And then after that, like sunrise is already moved to a different time. Like it's already 10 minutes changed every day. Whereas like if you check out sunrise on around June 21st, really there's not much change on a day-to-day basis. So, anyways, I hope that makes sense, because then when you keep looking at the other half of the graph, right here, the slope is negative. Why? Well, when you consider the amount of daylight you have, the change in daylight, not how much daylight you have, but the change in daylight over time, well, you lose how much daylight there is, right? Every day you lose a few minutes of sunlight until you get down to December, where you're down to like, only, what is it, a couple hours a day of sunlight. So this is obviously not a graph for like Southern Alberta, because we don't have just like 1 hour a day of sunlight. But I thought this was a good way to help visualize it. Okay, the last thing I need to talk about are some alternate notations. Many of these are you'll see over the course of your calculus career. The more you take calculus, the more of these you'll see. I'm going to probably use two. These will be the main ones I use. I'll use f prime x with a little prime notation up in the corner. But I also like this notation right here, which is written as d over dx fx. This is a notation which says you're going to take the derivative, and that derivative is going to be with x variables. That's kind of what this means. You're going to take a derivative, and that derivative will have x variables in it. That's what this notation means. And this is often called Leibniz. Leibniz. Oh my goodness, I can't even spell it. Leibniz. After, I believe his name was Gottfried Leibniz. I hope I'm saying his name right. I feel really embarrassing if I'm saying this poor guy's name wrong. Anyways, we call it Leibniz notation because back in the, 1700s, I think, when Sir Isaac Newton was around, Newton and Leibniz were both known for creating calculus simultaneously but independently. They did it basically right at the exact same time, only they didn't work together. They didn't copy off of each other as far as we know, but they both kind of were working on the same concepts, and one started using one notation, one used the other notation. And I personally like Leibniz notation, so I'm going to be using this sort of thing. We use d's and dx's, but it means the same thing. So, okay, the last thing I got to talk about is where you actually can differentiate. And this is kind of another verb we'll use, differentiable, where you can find a derivative. You can find a derivative pretty much anywhere as long as the function exists. If there is a function, you can find its derivative, because its derivative is its slope. But there's a few things we can't do. Okay, if you have a graph which has like a corner, you really can't find a slope right here, because it has to be like a smooth curve, and you're looking for the derivative right here. If it all of a sudden just came to a point and stopped, you really can't find a derivative of a point, because where would you draw it? Would you draw it there or there or there? So if you ever have a corner, it doesn't work. And corners you might find on, say, like an absolute value graph. So you really can't differentiate an absolute value graph at its point. If you ever have a graph that has some sort of jump from one section to the other, that wouldn't work. A good example of that would be your typical reciprocal graph, where it goes like this, where it has to jump from being down here to up here. You really can't differentiate at that point, because you can't find the slope at 0, because, well, it's right here and it's right here. That doesn't really fit. And at vertical tangents, the definition of that would be like where the graph just kind of starts on a dot, like say your graph of the square root of x, where it just starts all of a sudden randomly. you really can't find a derivative at that point either. So I should point out, differentiable, to be able to find a derivative, is not the same as continuous, but there's some similarities there where there's some graphs that aren't continuous and then therefore also you can't find a derivative of them either. So let's talk about these graphs here. Where would you not be able to differentiate these functions? Like, where would a derivative not be possible? This graph would be a square root graph of x plus 2, which would be slid over this way here. Something like that, right? You could find the derivative right here. You could find the slope right there. You could find the slope right there. But you know, the one point you couldn't find the slope at here is when x is -2. That's not really reasonable. You couldn't find the slope right there because really the graph doesn't exist anything lower than -2. For an absolute value, we could draw that little V shape right there. If I asked you for the slope right here, well, I mean, it would be just 1, I guess, right? Because really there is no curved line to work with. It would already be linear. If I asked you for the slope right here, it would be -1. But if I asked you for the slope when x was 0, you really can't do that because it's coming to a point at that point. So you can't actually calculate the derivative at that one specific point, basically. Okay, that's my set of notes. What am I up to for time here? Just looking back here. Okay, it's been 41 minutes. I would highly suggest looking back over a couple of examples. The main ones being this example here where you sketch a graph of the derivative. Rewatch that example or ask me to help with it. Hopefully my examples of where this applies to the real world, where we talk about like daylight per time, or way back here where I did an example of how much work there is over time, or how much money you make over time, wherever that graph is, your money versus time. Hopefully you get the idea of how these are going to apply going forward, because now we've gotten to the meat of the matter. Now we know, now I can show you why calculus is needed for accounting, why it's needed for engineering, why it's needed for the sciences, or at least how it's used. You may never use it, but hopefully you can see how it is useful to someone somewhere. And then the last thing is hopefully you get the idea of how to utilize this formula right here. I've done about 4 or 5 examples. Hopefully you've also done the one example off the first assignment where it's the same thing we were doing with limits, only you don't get to plug a number in. You got to work with generic x and h values. Ideally, all of your h values should be able to cancel with the h on the bottom at some point, and you should be able to plug in h as 0 and get yourself an equation. If you start with a quadratic, your derivative will be linear. If you start with a cubic, your derivative will be quadratic. So a derivative then, maybe this is a good place to stop and reiterate this one more time. A derivative is an equation which can find you slope. So if you want to find the slope at 1 minute, then plug in 1 once you have your derivative. If you want to find out your slope at 10 minutes, then plug in 10. Right? If you're an investment trader and you want to find out what the day-to-day change was on day 10, find the derivative of money versus time, right? And then plug in day 10, and that will tell you how much day-to-day change there was from day 10 to, I guess, day 11. Right? Okay, I'm going to stop now. Like I always say, ask me questions, email me. Let's chat on our designated times to chat, and hopefully this one made sense. So talk to you later.